Well, I am Aldo Rodriguez Puebla, and today I will present you a new model that we are doing about doing the semi-empirical modeling for the galaxy hello connection that we call Empire. And well, first, thanks to the organizers for letting me the opportunity to present my work in this at this meeting. And well, my name is only on the presentation. There are a lot of collaborators about this work, and one of them is here, Vladimir Avilaris. So let's start. So um, we have several ways to study the galaxy hello connection, and to study galaxy evolution. So in here, I tried to just summarize with this picture what are the main trends that we use to study galaxy evolution. So we have on the left side the empirical modeling for the galaxy evolution, in which we have a galaxy distribution population where using SEDs or using the spectroscopy or the photometry information from the galaxies to infer how the galaxies assemble due to archaeological studies. Well, see Vladimir's talk later today. And then we have, which are purely empirical methods to study galaxy formation. Then we have the theory in which we need a structure formation model, perhaps lambda CDM, other models can be used as well. But in this case, I will just focus on the lambda CDM. And from the lambda CDM, we try to model all the physics for the galaxy formation. So we have two ways to do that, semi-analytic models and hadron simulations. Then recently, in the last 10, 15 years, a new model has been born in order to study these two galaxy evolution in a more semi-empirical way, in which one tries to connect the galaxy population with the structure formation model without modeling any physics. Okay. So everything that is, all the information that is obtained from the galaxy hello connection is purely empirical. But then we can use this information in order to get the physics behind the galaxy formation. Okay. So this is the goal for the semi-empirical model. Build a model that is consistent with the observations and the cosmological structure formation model without introducing any physics. Well, this will be very useful, as I said, because we can project the observations into a direct interpretable cosmological framework of galaxy formation. So here I just put in some schematic way in which we will have a machinery which we call the galaxy hello connection. Well, this is my brief introduction about what is the galaxy hello connection and the semi-empirical modeling. So there are several ways to do this, and I won't describe in detail this, but I just want to emphasize that despite all these methods to connect the galaxy to do the galaxy hello connection, one of them is the Abundance machine, which is most famous. Others are the hello connection distribution models. The point here is that despite all these models, there is a very nice consistency between them. They use different observables to constrain this galaxy hello connection, clustering perhaps, others just galaxy star functions. But the main point is that we, despite all the uncertainties in the observables, we have a very nice picture about what does the galaxy hello connection looks like. Okay. So in particular, there are some models in which, using the merger trees of the dark matter halos, the assembly history of the dark matter halos, and using some parameterizations for the stellar to halo mass relations, we can put the galaxies within the merger trees and then infer a lot of properties of the galaxies. Like, for example, the evolution of the galaxy stellar mass function, which is in the top right of this slide, the star formation rates of the galaxies, and the cosmic star formation rate of the galaxy. So we can use these observations in order to actually constrain what are the stellar to halo mass relations in order to connect halos with galaxies. So here I'm showing some previous work that we did. I think you cannot see very well the axis of these figures, but for example, in the top, in the bottom left of this figure, we see the assembly history of the dark matter halos This is the y-axis. The x-axis is the redshift, 1 plus k. And then it is color-coded by the star formation rate of the galaxy that is hosted by this dark matter halo. So you can see that the most massive halos that we believe that will host elliptical galaxies, you can see that around redshift 2, redshift 3, they peak the star formation history across all the time. So you can, from this figure, you can read off what are the star formation histories for the continuous of the dark matter halos. This is just an average quantity, but you can read off all the star formation histories for the halos. And then from the right, and on the bottom right, you can see also the same thing, but now as a function of the stellar mass of the galaxies. So this galaxy halo connection, despite being very simple, it tells you a lot of how galaxies evolve, and actually you can reconstruct the star formation histories of the galaxy. So it becomes a very powerful tool. But the figure that I showed you before, it was only for all the galaxies. I was averaging over all the galaxies. We didn't know anything about whether the galaxies are star-forming or quiescent galaxies. We know now, at least at redshift 0, that galaxies distribute as star-forming and quiescent galaxies. If we plot the star formation rate versus the stellar mass, we can see that they divide into a big population. Okay, even to higher redshifts. Okay, and also we know that the stellar to halo mass relations are different for quiescent star-forming galaxies. Here I'm showing some previous work that we did, in which we found that the halo masses of star-forming galaxies are smaller than the masses of quiescent galaxies. So then we need to implement this in order to get a more realistic model in the galaxy halo connection, which most of the models, they don't do that. So with this motivation, we have now a new model, which we call Empire. And the motivation by calling Empire is because we're now trying to model different galaxy properties into the dark matter halos. In particular, here I will show some results about how to connect galaxies, supermassive black holes to dark matter. So these are the two simulations that we are using. One is a box of 1 gigaparsec. Another one is a box of 200 megaparsecs. I will be very brief on this. And then very nice introduction by Antonio. He showed that there is this secondary property of dark matter halos. In this case, I will use that property that at a fixed halo mass, that has a larger Bmax or B peak that I'm showing here, will be older halos, marked cluster halos. Halos with lower Bmax will be younger halos and less cluster halos. So Empire uses information in order to connect the star formation rates to the galaxies. So halos that are older are more likely to have a younger galaxy with a lower star formation rate. And halos that are younger are more likely to cause a high star formation galaxy and a younger galaxy. Yeah, that's the core. We also assign supermassive black holes. We basically divide into two types of galaxies that host supermassive black holes. Galaxies that are star-forming galaxies will have more likely an AGN or a quasar, and galaxies that are quiescent will likely to host more another type of model, perhaps a radial mode AGN. We don't know about this. We just call it the X mode and within the model, but we can parameterize that. So I will go very fast in here. So the observational constraints, we use the evolution of the galaxy mass function, the evolution of the quiescent fraction as a function of redshift from redshift 0 to redshift 4. Also the fraction of quiescent galaxies divided into centrals and satellites, the fraction of satellite galaxies is shown here, the cosmic star formation rate, the evolution of the star formation rate main sequence of the galaxies, and this is the mean of the star formation rates divided into star forming, quiescent, and all galaxies. You can see by I hope it is obvious by the colors that I show here, and all the lines that I'm showing are the fits to the model. So here is also the evolution of the size to stellar mass radius from redshift 0 to redshift 6. and evolution on the left of the quasar luminosity function and the fraction of obscure AGNs as a function of redshift. Well, all this battery of observations have been used in our constraint model. So, and also the relation of black hole mass between the ratio of the stellar mass to effective radiant. Okay, so I will show you some results. Here we have on the left the evolution of the stellar to halo mass relations in comparison with the recent result by Peruzzi 2019. Our results are very consistent to the one of Peruzzi. And these are the results that I would like to emphasize here. The clustering. The clustering, when this is a prediction of the model, we obtain the clustering of the divided into star-forming and quiescent galaxies, and that is consistent with the observations for low redshifts, high redshifts. And also when we try to split the main sequence as the figures that I'm showing here. On the left, you have the specific star formation rate versus stellar mass, and the different areas are the regions where we calculate the clustering and we compare to observations. Lines are our model, and the circles are observations. When we made dots and the star formation rate, and when we made grids and the star formation rate. And it seems that the model is capturing all these trends with the observations, which we are very happy with. And I will skip this, and I will let my summary here, and I will take more questions. There are a lot of things that we can discuss more later if you want, but
okay. Thank you very much, Antonio. We think we have a question of Felix Mirabel. So, you want to start, Felix, with the question?
Yes, very nice talk. Thank you. I have a question. As you know, now has been recently reported the discovery of black holes in quasars at redshifts greater than 7.5, about 10 of them, with masses of about 10 to the 9 solar masses. How do you fit the existence of these supermassive black holes, so massive, with masses equivalent to the masses of the black hole in Messier 87, so early in the universe? Would they have been formed before the stellar structures and evolve very rapidly, much more rapidly than the stellar structures in galaxies?
Yeah, yes, this is a very good question. So within the model, what happens is that these kind of supermassive black holes will form in very dense areas of. So basically, we are just projecting what happens with the dark matter halos. So in terms of the dark matter halos, we will have halos that are very concentrated in a very dense environments. In those cases, it's very strange to find these kind of supermassive black holes in our model. That's true. But they form in these environments. That's what I can say from the model.
Okay, thank you.
Okay, we have time for one last short question. Okay, so I have a small comment related to Felix's question. Not the model. I don't know the relation with the model that I have shown yesterday. Interestingly, the Felix question is that if you account for the quantum nature of the dark matter particle, for example, if you choose fermions, you can have there is a possibility that the halo, when born in the high redshift universe, let's say C10, the halo can born with a core halo nature or structure, and it's interesting that this core can collapse and can undergo a gravitational collapse and collapse towards a supermassive black hole without a prior star formation rate. So this I think is such an interesting point to consider. Maybe try to make an end-by simulations with the quantum nature.
Yeah. So directly from the gas collapses and forms that the supermassive black hole is. That's what you are saying.
No, it's only from dark matter.
Only from dark. Okay. Wow.